Hi everyone, it's me, Carolyn, and in this lecture we are still going to be working in chapter 5. This section is 5.4. In here we're going to look at some contingency tables and also discuss the idea of a given statement or conditional probabilities. And we'll also be looking at a few more trees, and we'll look at turning them into what we call probability trees, and go from there. So let me start by sharing my screen. And we've got, also have my calculator ready for us. So when we're ready to do some calculator work, I've got it right here with me. But we're going to start with a contingency table. A contingency table just means a table in which you have different things broken down. For example, it just kind of has the information in this table here. And what this is I've got a container. It contains some pieces of paper, and each piece of paper has either a circle or a square drawn on it and colored in. So like we have 7 pieces of paper that have a red square on them, 3 yellow squares, 6 blue squares, and so on and so forth. I did put the totals down there to make it a little bit easier for us to do some of this work. What we're going to do is we're going to take one slip of paper out of this container at random. And we want to calculate what is the probability that this piece of paper has a red figure on it. So if you remember, when we're talking about probabilities, it's a number of ways that can happen out of the total number of ways. So we do have a total of 31 different pieces of paper, and we're looking at what is the probability it is red. Well, that is going to be our 15 red ones out of our 31. I am going to just leave them in fraction form. You can, if you wish, turn them into decimals by taking 15 and dividing it by 31. But leaving it in fraction form can kind of help you remember where those numbers came from. All right, probability it was yellow or had a yellow figure drawn on it. That is our 7 out of the 31. The probability that we had a square is 16 out of that 31. And the probability that we have a red square. So now we're being a little bit more specific. So we have to go into the table and find we have that 7 red squares out of our 31 pieces. Okay, so that gives us a little bit of familiarity with how to work with these contingency tables, these tables that have information on it. Now we do have something a little bit further on called conditional probability. And we start with 2 events, E and F are events. This symbol, this is going to be a straight up and down line, is read as the probability of E given, so that straight up and down piece F is true. So what we does is it tells us that F has already happened, or it's an information that you already know. So we're going to do some here, and we're going to do that. The probability that it's yellow, given we know it was a square. So it kind of tells us, I've got a piece of paper and I tell you it's a square. So that means we don't need to worry about the circles anymore. So we're just looking at these 16 squares. And out of those 16, 3 of them were yellow. So this kind of restricts our sample space into what we look at. So no longer looking at all 31 pieces, because I've already told you it's a square. So I already know that we're only looking at those 16 pieces of paper. Okay, let's do another one. So we're going to do probability of the circle given it's red. So given you know it's red, here's our red. I want to know probability it's a circle. So that's going to be 8 out of those 15. blue, given it's a circle. What's the probability it's blue, given it's a circle? So we know it's a circle. There's our circles. So out of our 15 circles, we want to know the probability it's blue, so 3. And again, we should reduce these down. We can turn them to decimals. I'm just going to leave them there so we can kind of see where those numbers are coming from, because sometimes that's more important than the actual decimal or actual reduced fraction. Okay, in general, I kind of want to talk about where these numbers came from. So if we have the probability of E given F, notice this bottom number, that 16 or that 15, came from the given part. So given the square, given the red, given the circle. So the probability given F, that probability piece is going to be on the bottom. The top number, so that 3, was our yellow squares. Yellow and a square. Red and a circle. Blue and a circle. So that top piece is that and statement. Okay. From here, we can do a little bit of algebra. And we can reduce this to the probability of E and F happening is the probability of E and E given F. So I could kind of reverse those around a little bit. I mean, I could have switched these two around if I'd wanted to. And this should be F given E. Yeah, let's change that so it makes more sense. Yeah, I've seen it both ways. So where it comes into play is going to be in situations like this. So we're going to draw 2 cards from a deck of cards. And this time we're going to not put it back. Okay, so we're not putting it back. So I want to put a king on the first and a queen on the second. So this tells me this is a and statement. So I can do king on the first. Well, the probability of king on the first is, I'll just write this out in words. And then we can multiply by the probability queen second given king first. That's where that general rule can come into play. So probability king on the first, well, that's 13 out of the 52. Or my 1 out of 13. Oh, there's 4, sorry. Ooh, 4 out of 52, which is 1 out of 13. And we're going to multiply that by the queen on the second, given king was first. Okay, well, there are 4 queens still in our pile. However, we no longer have 52 cards in our deck. Because we pulled that king the first time, there's only 51 cards left. 4 out of 51. That's not. So multiplying those together, I would get 4 out of whatever 13 times 51 is. 663. Okay, so you'll notice this given, since we didn't put it back in, that changed our deck. We no longer had 52 cards in there, we only had 51. Let's do another one. Probability of getting 2 hearts. Now there are 13 hearts in the deck, and to get 2 of them, we got to get a heart and then a heart. Again, we're not putting it back in. So it's going to be the probability of getting a heart on the first, which is 13 out of that 52. And the probability that we get a second heart. But we already know that the first one was a heart. So there's only 12 left in the deck and 51 cards left in the deck. So we could have reduced this a little bit down before. Because that 13 over 52 does reduce down to 1/4. This does reduce down to 4 over 17. These will reduce, so we'll get 1 out of 17. Doing a little bit of our algebra that we have. Okay, I'm gonna draw a tree. Okay, we have a box that contains 7 purple and 3 green. So I'm gonna use P for purple, G for green. And we're gonna draw two balls from this box, and we're not gonna put it back in. So I'm going to first of all draw my tree, because it's gonna help me. So if I draw, this is the first draw. Now you could draw all the branches together, like we have 7 purple branches and 3 green branches, but I'm gonna just say we either got a purple or we got a green. I'm gonna put the probabilities in at each stage. This will turn it into a probability tree. So we had 7 purple and 3 green, which means probability of getting a purple at this stage was 7 out of 10. Probability of getting a green is 3 out of 10. Notice adding these together gives me 1. The sum of all of our probabilities will add up to 1. From here, we're going to draw another ball. Again, it's either purple or it's green. It's purple or it's green. I'm going to put the probabilities in, but if I'm here, that meant my first ball was a purple, which means there's only 6 purple balls left in the bucket, and there's 9 total balls. I'm going to reduce that down 2/3. Here, either it's green, again, the first one was purple, so I still have 3 green balls, but there's only 9 left. So that's 1/3. Notice those two will add to 1. Got a green one first. Probability it's a purple. Well, green first. There's still 7 of our green balls that are purple out of the 9. Here, 2 out of the 9. Because we only had 9 balls left. 1 was here. This one was green, so 2 greens left. Those two numbers add together. Notice also these are conditional based on what happened here. Okay. Now the thing that you'll see is when you go across here, you're going to get that purple combination. The probability of getting a purple is that purple on the first multiplied by the purple on the second, which is that 2/3, which I can do a little bit of reducing here. I get 7 out of 15. Here's my purple on the first and green second, so my purple and green. So I'm going to start hearing the word and I'll be associating those complicated multiple step pieces with multiplication. That's 7 out of 10, 1 out of 3, 7 out of 30. Here I'm going to have a green and a purple. So green and purple, green on the first and purple on the second draw. 3 out of 10, 7 out of 9, or 21 out of 90. And the last one is our green and green. Not that I would need to calculate the probability of each of these branches, but it might help what comes later, depending on where you're going. A little bit easier to have this done. So I get 1 out of 15. Okay. If I turned these into decimals and added all 4 of these up, you would get the number 1. Notice these 4 things are not equally likely. Yes, we have 4 outcomes, but they are not all equally the same. Okay, unlike when we did some of those other trees where we had our head, tail, all of those were the same. They had the same possibility of happening. If you were to draw out the complete sample space, you would have a lot of P possibilities because we had 7 P's to begin with and then 6 P's. So we have technically 42 different P's out there because we have 90 different possibilities, 10 possibilities for the first, 9 for the second. And this will get connected when we do our last unit where we start talking about how many ways something can happen. Okay, but we want to find the probability that we had both balls are the same color. So that means we are purple, purple, or the green, green. These two are disjoint, mutually exclusive, have nothing in common, so we can take and add those two together. 7 out of 15 plus our 1 out of 15. 6 out of 15. All right. If you start hearing yourself say the word or, when we have disjoint, we can add. It's being across those branches and we will multiply. At least one ball was purple. So this one, or this one. So we could add all 3 of those together, or since these all add to 1, we could do 1 minus the no purples and get that value. All right. Green was drawn second, given the first was purple. This was kind of a little bit trickier. It's not these guys here at all, but it's kind of like, okay, I tell you the first one is drawn was purple. And I want to know what is the probability that our second one is going to be green. So I already told you we were up here, and I want to know what is the probability that we get that. That's that number that's right in here. That's that 1/3 that's sitting in there. These are a conditional probability based on what happened first. Okay, here's probability of green on the first and purple on the second. Green and purple. Green and purple is this one right here. Okay. This one is tricky. This one's saying, what's the probability we get a green on the first, given it's purple on the second? Well, purple on the second is in 2 spots, here and here. So out of these 2 branches, I want to know probability was green on the first. So this one, we can use that formula that we had. Probability green first and purple second, given probability purple second. Okay. So again, thinking about how this conditional stuff works. So purple on the second was these 2 branches. So I want the and statement on top, that 21 out of 90. That's my green on the first and purple on the second. Given purple on the second, which means I'm here or I'm here. So I'm going to have to add those 2 together. And this is where I'm going to get my calculator to help me out a little bit. I'm going to have it do the bottom 7 out of the 15, and I'm going to add my 21 out of 90. Or you could easily go to decimals, which may have been easier, but that's all right. I get 7/10 when I add those 2 together. So if I take 21/90, which would have reduced, and divide it by 7/10, I get 1/3. Okay, notice it is not the same value we have sitting there. It's a little bit different. So I tell you, basically, it's like you pull out a ball in one hand and then you pull out the second one and you say, hey, it was purple. What's probability that this one here is that green? And I've got that it turned out to be 1/3. If I did that correctly, 21/90 divided by 7/10. All right, we're gonna do one more. And I want to show you this one simply because it is used in the medical field. And it is kind of hard to see. So I'm going to draw a picture once we're all done to show you that it's kind of eye-opening. All right, let's say we have a very rare disease. I don't know what disease this is, but let's just say it's very rare. And that having this disease, only 1 out of 1,000 people have this disease. Okay, so that's like 0.001. And I am going to use decimals in this one. Feel free to use decimals when you're working with fractions as well, whichever you feel more comfortable. And further, we're going to have a test for this disease. So basically, you go in and they give you this test, whether it be a blood test, urine test, nose swab test. We don't know, but it's 99% accurate, okay, at detecting the disease when you have it and telling you that you're healthy when you are healthy. So we're going to draw the probability tree for this thing. So here I am. Okay, that's me or the person. And when we go in to have this test, we already know, or we don't know it, but you are either healthy or sick. So I'm going to go healthy or sick. Okay, the probability that we are sick, I'll do that one first, is this 0.001. 0.001. Okay, which means the probability that we're healthy, that's everybody else, is going to be that 0.999. All right, so now we go in and we take this test, whatever this test is. And this test is going to come back either positive or it's going to come back negative. Positive would tell you you're healthy. A negative means, I take that back. Positive comes back positive, that means you're sick. A negative tells you you're healthy. So if you are healthy, the correct response of your test should be the negative. So since it's 99% accurate, this 99 is going to be on that negative test. So that means here is a 0.01. Because either you're negative or positive. Negative means you're healthy. Positive means, or positive saying that you're not healthy. All right, so if you were down here and you're sick, the correct response to this test should be a positive result. And here's my 0.01. Okay, these people up here, this positive and getting a healthy person, that's considered a false positive. So if you've ever heard the term false positive, that's up here. That's coming back saying, hey, you're sick, but you really were healthy. So it's falsely saying the result. Down here is our false negative, meaning the test came back negative, but it was incorrect because it's saying you're healthy, but in fact, you really are sick. All right, and instead of spending all the time filling out all the different branches, I'm just going to go through a few of these and go through and say, okay, let's say we have, what is the probability that we had a healthy person and they received a negative test? So healthy person and received that negative test. So that's going across the branch. That word and, 0.999 healthy and the negative test, the correct test. Multiplying those together, It's 0.98901. All right, let's calculate the probability that we received a positive test. So in other words, the test came back positive, regardless of being healthy or sick. So the positive tests are up here and down here. So we have two branches. We have our healthy positive people and positive, or we have our sick and positive people. So I'm going to do some calculations here. 0.999 times 0.01. I'm going to add these up here, 0.00999, adding that to 0.00099. This gives me 0.01098. Okay, so you go, no matter if you're healthy or sick, you go in. The probability that the test is going to come back positive is this little bit. So roughly 1 out of 100 that you get a positive test. Okay. Here's the question. What's the probability that you are sick given you have that positive test? You should think that that should be pretty high. Because if you get a positive test, that's telling you, the test is saying, hey, you've got this rare disease. We need to worry about it. So, but what is the probability that that is actually the case? Okay, to figure that out, remember, it's a conditional. So we need that sick and positive. So we're basically saying we got a positive test. So we're on one of these two branches. What is the probability that you are on that sick and positive test? So that's going to be sick and positive out of the positives. So sick and positive, that's my 0.001 times my 0.99. And my positive, that's what I just calculated up above from before. So that's why I kind of did a 0.01098. So multiplying these two together, and I've done that here, 0.00099. And that's that calculation here. Where'd that come from? That 00999. Okay. 0.00099 divided by 0.01098. 0.0901. So the probability that you are sick, given your positive test, is only 9 out of 100. You would have hoped it was a lot larger. Okay. So how in the world can that be the case? So you're only about 9 100ths. And so what I'm going to do is kind of draw a picture to show you that even if you get a positive test, the chance that you are sick is still very, very small. And that's because our test that we have does have a lot of false positives. Okay, so let's just look at this picture. Okay, so let's imagine that we have 1,000 people in here. And I'm choosing 1,000 because it just is a nice round number. Also big enough because we have this disease that 1 out of 1,000. So here you are. That's our sick person. Right? So we have 1 out of 1,000 people that actually has this disease. So that means we have 999 healthy people. Okay. Our test, let's just say we gave the test to everybody. Our test is accurate 99% of the time, which means that 1% of the time it is inaccurate. So if I'm looking at these 999 people and I want 1% of them, that means I get 9.99, about 10 people would test positive. Okay, they'd get an inaccurate test. So let's put these 10 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 people that have a positive test that are really healthy. And let's just throw our sick person in there with them. And let's say he went and he had an accurate test and not worry about the minimal people that chance that he would have gotten that incorrect test. But now we have 11 people here. 11 positive tested people, positive tests. And only 1 out of those 11 is in fact sick. Well, that 1 out of 11, if I do my math, is at 0.09. So that's telling us, even if we have a positive test in this case only, that we might not still be sick. Hence, historically speaking, way back when AIDS came around and the test wasn't all that accurate. So just because you had a negative test or a positive test, they wanted you to retest later on down the line, because the fact that you would get that inaccurate test twice in a row is it was, and sometimes they'd even have you go a third time. And this was because our tests were not completely accurate. The tests for things have gotten a lot better on certain rare diseases, but a lot of times when they will have these sick people or these positive tests, they'll have you retest, or they'll have you check something else again. They don't automatically assume that you have these diseases. When you have cancer screenings, they check it and then they'll check something else. When you do other tests and they check it and they find something, they check something else, because they want to make sure if they're going to tell you you have these terrible diseases, that they are accurate. Okay, we have one more section in chapter 5, and that tends to be a very complicated section, and it's kind of trying to find the number of ways something can happen. So for example, when we had that problem where we had the purple and the green balls, how many different possibilities could we have? Well, if we numbered all of our purple balls and we numbered all of our green balls, it would turn out we would get 90 different possibilities for these, and a lot of them would all look the same because we'd have a purple green or a green purple. And that's where this next section comes into play. And how do we count the number of ways something can happen? If I have 3 coins and I'm flipping them, how many different outcomes are there? You know, and if you're trying to list them all, do you have them all? So it kind of helps if you know how many you're supposed to have. But that is in our next video. So I am going to stop recording here, and I will tell you to have a great day, and I'll see you in the next video.